There are two major steps in BFS. They are selecting a node and exploring its unexplored childs. The childs has not been explored yet. So there are V vertices, this is cardinality of V, but I will consider it as V, which is the number of V is the set of the vertices or nodes in a graph or a tree. A tree is a graph true. So this cardinal to V represents the number of total number of nodes in a graph, and the cardinality of E is the number of edges in a graph. So the time complexity of BFS is if there is a normal graph or a tree that is undirected, then we process each vertices at most once, and we have to process each edges at least twice, because consider if there are two nodes like A and B and there is a edge between them, then whenever you select A, you have to check the node AB to find out the child B, which is a child of A. And if you select the node B, you have to check this edge AB again to find out the child of B. So if the graph is undirected, every edge is checked twice. So every edge is processed twice. So the time complexity becomes big of B plus 2E, which we can write as big of B plus E, because we can ignore the constants. If the graph is complete, then there will be B into B minus 1 divided by 2 edges in that graph. So from here, after replacing this E, we can replace it with B square, because this is ultimately big of B square. So number of vertices B, number of edges is B square, we can write, because we can ignore these constants and things. Those things we can ignore, the lower power terms, lower degree terms. So for a connected graph, the time complexity becomes big of B square. So we can use two types of data structure to store the information about the edges in a graph. We can either use the adjacency list, or we can use the adjacency matrix. If we use the adjacency list, we have to store less entries compared to the adjacency matrix. In adjacency matrix, we have to keep, like, if there are B vertices, we have to keep B square entries, so which will take more time to check. But in the adjacency list, if there are only two edges, so consider if the node A has two childs B and C, so there are two edges, so you have to just store these two edges. But in adjacency matrix, for A, you have to store all these entries here, as you can see. So time complexity becomes higher if you use an adjacency matrix for storing the information about the edges. So if you use adjacency list, then the time complexity is big of B plus E. But if you use adjacency matrix, the time complexity will be same as for a complete graph, which will be bigger of B square, because there are B square entries. And for a tree, if the tree is also a graph, but in a tree we can represent the number of nodes using the branching factor and the depth of the tree. So for a tree, the time complexity, if we generalize from the idea of a graph, the number of vertices is V. We have considered the n number of nodes in a tree, so we replace this V with n. And for a tree, the number of edges is 1 less than the number of vertices, so it is n minus 1. So ultimately the time complexity is big of n, which is the number of nodes in that tree. Now n can be written as b, which is branching vector, to the power d, the depth of the solution. I have written it as solution, it's not solution, the depth of the tree. And now I will talk about the space complexity. The space complexity of a BFS algorithm will be big of b to the power d, because when running the algorithm you have to hold at most this many nodes in the memory. So in this tree, look at here, when running the algorithm I had to store this GFED. There came a situation in which I had to hold these 4 nodes in the memory. So we can write this number as, for a tree, it is b to the power d. So space complexity of BFS algorithm is b to the power d.